All right, guys, so we're going to jump into and talk tonight about chi-square. So what are we on? Are we on week 5? Is that what we're on?
Yes.
All right, makes sense. All right, so in week 5, one of the competencies that we're working on is how to do a chi-square distribution. And essentially, what a chi-square allows us to do is assess if there is a significant difference between the distribution, excuse me, the distribution of our data between what we observe in our data versus what we expect in our data. So let's look at it in 2 or 3 examples of how we would do a chi-square test to really kind of understand what the homework assignment is asking us to do. So I don't have fancy notes like on some of the YouTube videos where you can actually draw on the screen. I have to kind of go old school, and so you actually just get to see my notes. All right, now the first couple of examples are actually going to kind of go along with what they did in one of the videos. And for me, guys, honestly, that's how I've learned to do a lot of statistics. There are some phenomenal tutorials out there. There are some phenomenal YouTube videos. And in part, what I'll do is I sit there and I actually do along with the video what they're doing, which is essentially what you would do in class, right? If we were working in a classroom environment and I were doing examples up on the board, you'd be taking notes and following along and doing it along with, correct?
Yeah, that's exactly what I've been doing.
Yeah. So that's what I encourage you guys and other students that go back and watch the YouTube videos. You know, don't just watch and say, oh yeah, that seems to make sense. Go through and actually write on paper. So that's essentially where these first 2 examples come from. They come from the video. So let's just kind of make sure you're not going to have time to keep up and write all this down, but you've got access to the YouTube videos. So let's go through the example that they gave in the YouTube video where we have 100 coins. We have 100 coins, quarters laid out on the table. Obviously, we flip that coin. We know from probability, what's the probability of getting heads versus tails? 0.5, right? So 1 out of every 2 times, we're going to get heads. 1 out of every 2 times of a flip of a coin, we're going to get tails. So in this example, we flip a coin 100 times. And we just randomly get 62 heads and 38 tails. If we would think theoretically, if we did this 1,000 times, eventually we're going to start to converge on the true mean, that probability of 0.5. Okay, but in this case, we did it 100 times randomly. We got 68 heads, 38 tails. And we want to know from a research hypothesis, is there a significant difference between the observed and the expected frequency? We know that when we write that out as the null hypothesis, which is what we're going to either reject or fail to reject. And those are our only 2 options, right? When it comes to a null hypothesis. We reject the null hypothesis or we fail to reject the null hypothesis. We don't ever technically accept the null hypothesis. So in this case, when we write the null hypothesis, we're going to say that there is no significant difference between the observed and the expected frequencies. And so one of the first things that we need to do is we kind of write out our observed versus our expected frequency table. So in this case, what we actually flipped for heads was 62 and 38 tails. Well, we know, given probability, how many times out of 100 should we get heads? 50. How many times should we get tails? 50. So in that case, then from there, what we do is we need to look at our chi-square formula, which is just the sum, meaning we're going to add these up. The sum, I think I've got the formula. I probably have it on another sheet. Oh, here's our formula. The sum of the differences between the observed minus the expected frequency squared divided by the expected frequency. So if this looks foreign to you, here's how we're going to solve for it. We just flipped 62 heads, 38 tails. We know the probability of getting heads is 0.5. So out of 100 times, 0.5 times 100, we should get 50 heads and 50 tails. Kind of intuitively making sense so far?
Yes, sir.
Anybody have any questions at this point?
No.
Okay. So then what we're going to do is we're going to subtract the observed frequency minus the expected frequency and square that value, and then divide by our expected. And we're going to do that for heads, and we're going to do that for tails. So if you took the time to actually work this out, 62 minus 50 is 12. 12 squared should give us 144 divided by our expected frequency. So 144 divided by 50. We're going to do the same thing for tails. So 38 minus 50, even though that's a negative number squared, that's going to give us a positive number. So 38 minus 50 is negative 12 squared is 144. So 144 over 50. So these are our two values. And our formula up here was just the sum of those differences squared divided by the expected value. So the sum of those, that's what sigma stands for, the sum. So we're going to add those up. So 144 over 50 times 2 comes out to be 5.75. That number is what we're going to have to compare with some chi-square critical value. And let me pull that up, because you need to know how to use a chi-square table. Should have had that pulled up. As I'm pulling that up, does anybody have any questions on that math there? None so far. Once we actually get to do this in SPSS, I mean, this is a pretty straightforward problem, but once we get to do this in SPSS, I mean, it's going to run that analyses in half a second faster. I mean, it'll be lightning fast. But I want you to see how this works. So, because even once you get that value that we just came up with of 5.76, once SPSS gives that to you, you're going to have to compare that with some value. So let me pull up a chi-square table. Those are my notes.
It's in the back of our book.
Is it?
Yep.
Tell you what, I can easily just do this. So as I'm pulling this up, Nicole, kind of walk us. Have you looked at that chi-square table?
Yes.
Let the others know what page number that's on, so if they're referencing it, they might have
898.
898. So if you have the book, go ahead and flip to page 898. That's being slow. All right, so if we're on page 898, critical values of chi-squares. So we need to know two things. We need to know our degrees of freedom, and we need to know our probability level. Now, essentially, in this case, our degrees of freedom is going to be n minus 1, the number of our groups minus 1. So how many groups do we have?
Heads and tails.
We have heads and tails. So n minus 1 would be 1. So we have 1 degree of freedom. And usually in this class and many social science, related courses, we're going to use a 0.05 alpha level. Unless you're specifically told some other alpha level. So in this case, we're going to set that at 0.5. I'm trying to do two things at once here. So if we go down degrees of freedom and then over to 0.5, what is our critical value?
3.84.
3.84. Yep, and we can see here with our chi-square probability table, at an alpha of 0.05 and degrees of freedom of 1, Yes, 3.841. So that's our value. That's how we would use a chi-square table. We just need to know our degrees of freedom and where we have alpha set. So let's remember that value, 3.84. So we go back to wherever my notes are. And what was the chi-square value that we just came up with?
5.76.
5.76. So let's figure out what we do with that value. Okay. So here's the question that I tell students to think about. Is our chi-square value, and we literally ask ourselves, is 5.76 greater than our chi-square critical value of 3.841? In this case, is it greater?
Yes.
Yes, no trick question there. If it's greater, okay, we reject the null hypothesis. So the way we would interpret this is we reject the null hypothesis. And what was our null hypothesis? That there's no significant difference. So we reject the null hypothesis that there's no significant difference between the observed and expected frequencies. So in other words, there seems to be a significant difference in our data, the distribution of our data. What if we would have come up with our chi-square value of 2.76? If we came up with a chi-square value of 2.76, how would we have interpreted our results? Someone?
We would have accepted it.
We said we don't necessarily accept. Our two options are we reject.
Reject to fail.
Yeah.
We fail to reject.
Fail to reject.
So in that case, is 2.76 greater than 3.84? If the answer is no, then therefore we fail to reject the null hypothesis that there are no significant differences between the two groups. That's kind of how that works. So instead of, well, let me pause before we go on to a second example. Any questions on how we calculated chi-square, how we ran the test, how we interpreted the results, how we compared that to the null hypothesis? Any questions on that?
No.
Okay, I take it your silence is that there are no questions. All right, sounds good. All right, example number 2. You guys want to do another one?
Mm-hmm.
All right.
Yes.
Well, even if you said no, we were going to do another one. All right, so the second example that they did in the video, instead of, and I like the 2 examples that they did because they're pretty intuitive, flipping a coin, and then in example number 2, rolling dice. So here, the individual had 36 die, and they were all rolled. We know that the odds of rolling any number on one single dice is what? 1 out of 6. So that's going to help us when we come up with our expected values. We need to know that. The probability. Ringing a bell from other weeks, talking about probability. Maybe a scary reminder. All right, so we roll the dice 36 times. Now, if we roll the dice 36 times, we're going to inevitably, most likely, probability is going to tell we're going to get different numbers. But these were the values that they came up with. They rolled 2 1s, 4 2s, 8 3s, and so on. All right. So their question that they were coming up with here, if we were going to set a research and a null hypothesis, they're establishing a research hypothesis essentially. So let's remind ourselves of our null hypothesis up here. We're saying that there is a significant difference. Our research, as researchers, we're saying that there's a significant difference between our observed values versus what we would expect to roll the dice. If we rolled 600 dice, we would expect that close to 100 of those are going to come up 1. Close to 100 of those are going to come up 2. So we're saying that these numbers look off. Our research hypothesis is that there's a significant difference between these expected values and these observed values. So our null hypothesis is that there's no significant difference between the expected and our observed values. So here, what we do, I mean, again, just our formula for chi-square, our observed values minus the expected values. We're going to square those and then divide every single one of them by the expected value. So in this case, I'm not going to walk you through all of the math here. When this is reposted, you can go back and you can work this and kind of compare your answers. So in this case, just for the ones, our observed is 2 minus 6. Square that value divided by 6. So we should come up with 16 divided by 6. We do that for all of our observed values. And what we should come up with is 9.6. Our chi-square value that we came up with here should be 9.6. Now let's determine our degrees of freedom. How many numbers, how many categories do we have minus 1? So in this case, it's 6 minus 1. So let's double check my work and see if I came up with the correct critical value here from a chi-square table. So our degrees of freedom is 5. We all on the same page there? All right, so we should have 5 degrees of freedom, and we're going to set alpha at 0.05 if we didn't already establish that. So we've got 5 degrees of freedom. We go down to our rows, 5, and then we follow that over to the 0.05 level. And we should get 11.07. Everybody seeing that in your chi-square probabilities table?
Yes.
All right. So that's what we're going to compare here. So is our chi-square value here of 9.6, is that greater than 11.07? No. Since the answer is no, we fail to reject. We fail to reject the null hypothesis that there is no significant difference. So intuitively, in other words, there's no significant difference between these, between the observed statistics and the expected outcomes. So there's a couple of examples if we were working through, flipping a coin or rolling the dice. We can do one more example. Let me pull that up. All right, you would not be asked to do this by hand in class, trust me. There's a good bit of math here, all right, for this one. But what we've already done through the first 2 examples, this would be an example of something that we would use SPSS for. But let's walk through it and just see if intuitively we can follow along with what this is asking us to do. All right, so I grabbed this example from Penn State University. They had an online statistics course. I was working through some examples. It seemed like a relevant one for our course. So I reworked the example, and let's just see where we go with it. So in this question, we're being asked, is gender independent of educational level? So they asked 395 students at a state university, what degree are you working towards? Are you working towards your associates? Are you working towards your bachelor's, your master's, or your doctorate? Okay, and here's the data that they came up with. All right, I'm not going to read all this to you, but you can see how this is broken down. There were 100 individuals sampled that were working towards their associates. Of those 100, 60 were female and 40 were male. Okay, and so on and so forth for the bachelor's degree, the master's degree, and the doctorate. So our research question is this: is gender independent of education level? All right, so we had our random sample. We want to know, is there a difference? So it's our research question. Let's look at and kind of wrap our head. What's the research question? What's the null hypothesis? Our research question, what we think is the researchers, are gender and education dependent on each other at the alpha level of 0.05? So given our above data, is there a relationship between gender of an individual and the level of education that they're currently working towards? We always state sort of the null hypothesis as kind of the opposite of that. So in this case, our null hypothesis that we're testing for is that there is no significant difference between the education level based on gender at the significance level of 0.05. All right, so that's kind of what we're working with here. So let's first wrap our head around how we would even come up with the probability levels. All right. So in this case, the probability isn't that at 0.5. The probability level is going to be set based on what our sample statistics are. So if we wanted to get about how many we would expect in each of these categories, so for example, how many females would we expect to be working on their associates, or how many males would we expect to be working on their master's degree? Well, that's based on our sample data over here. So in this case, in order to get those probabilities, we need to take the total, in this case, total females divided by our total number of individuals in our sample. So 201 divided by 395, we get a probability, that'll give us our probability of 0.50886. For males, all right, 194 divided by 395 gives us a probability of 0.49114. Any questions about figuring out our probabilities level for males and females in this example?
Yeah, I don't have any idea where you came up with that number.
Okay, if we flip a coin, makes sense that probability of getting heads is 0.5.
Yes.
Probability of getting tails is 0.5. In this case, we can't just say that intuitively the probability of a female being working towards associates is 0.5 because gender is either you're either male or female, so it's 0.5. No, that's not our probability level. We know that even in the population of the world, that the split between males and females, the number of males and the number of females, is not exactly 50-50. It might be 0.508 males, 0.491 for females. It's based on the data that we collect. So in this case, we've sampled 395 students. That's our entire sample. Of those, how many were female? 201. Of those, how many were male? 194. So we would expect, given those frequencies, that distribution of our data, that 201 divided by 395 is going to give us what our expected value, our expected probability of females in the data. For males, it's 194 divided by 395. The probability of any one of these categories being male is at a distribution probability of 0.49114. So what do we do with that value? Well, here, we're going to come up with our expected values. You know how we did that over here, for example? We came up with our expected values for rolling our dice.
Yeah, those were easy.
Yeah, those were easy. It's intuitive. But sometimes our research question isn't as intuitive as flipping a coin or rolling dice. Okay? Right?
Yeah.
I mean, sometimes we're going to be asking research questions that are a little bit more complex. So here's a research question that's a little bit more complex. Okay, so just for the sake of moving on, because we've got a little over 7
You're
minutes.
fine.
What's that? Just trust that this is right, okay? As we get more practice with this, hopefully it's like throwing, you know, enough, excuse my language, enough crap at the wall. You know, some of it's going to stick over time, right? So just trust that this is right. We'll work with it more. All right. So these are our probability levels. Well, what do we do with that? So just like we did with the dice, we need to come up with our expectancy counts. So how do we calculate that? Well, we knew that up here, for example, we had 60 females working on their associates. Well, we need to get an expectancy count. So that's going to be 100 times our probability. So 100 times 0.5886 is going to be 50.886 females out of 100 are going to work on their associate's degree. 100 times 0.49114, we would expect that randomly out of 100, that 49.1114 of people working towards their associates are going to be males. And if we do that for each of our educational categories, again, so like for our bachelor's degree, we had 98 of them. If 98 times our probability level, 98 times 0.50886, we would expect females working towards their bachelor's that 49.868, well, that should have said 886. If just a little over 49 of them are going to be female. 98 times our probability for our males, the 0.49114, that out of 98 of them, that 48.132 of them are going to be males, okay? We do that for each of our categories here. And you can go back, you can kind of work this and make sure that these values here that I'm coming up with, these expectancy values here and here are all right. I can guarantee you they are, but go back and work it. Well, what do we do with those? Just like we did back here with our dice, well, now we subtract these from one another. Our observed minus our expected. So that's what we do here. Our observed for each of these data, so 1, 2, 3, 4, 5, 6, 7, 8. We have 8 values that we're going to come up with. So we just said for our females, all right, for our females, there were 60 working on their associates. So you see here, 60 minus our expected. What do we come up with for expected? 50.886. So 60 minus the 50.886, that value squared, divided by 50.8, and that, again, that should be 886. I did this in Excel, so I know that these numbers are all correct. So don't mind if when I have these typos there. You do that for each of these expected values, the observed minus the expected squared divided by the expected. And you should come up with these values here. And remember, so our formula is, it's just the sum of those, right? So we add all these up. So this row here, add all these values up, and you can double check my math when you go back and work this. The females, for the total for the expectancy, for the sum, should be 3.932. For the males, that should add up to 4.0739. All right? We just add those up. That should add up to 8.006. Well, what is that value? It's the same as we did over here when we calculated our chi-square value. So that 8.006, what do we do with that? Well, again, we're going to compare that with some sort of a chi-square critical value. In this case, our degrees of freedom because we have, I mean, this is a little bit more complex of a study. We have 2 different groups and 4 different categories. So it's a 2 by 4. But so essentially our degrees of freedom, and just trust that this is right. How many rows do we have? Well, we have 2 rows, females and males. So this formula is 2 rows minus 1 and columns minus 1. And then just multiply those by each other. So in that case, it's 2 minus 1 is 1. And 4 minus 1 is 3. So what is 1 times 3? 3, right? I know that, I mean, if you're not getting it all the way, just remember, go back and rewatch, go back and rewatch. So our degrees of freedom is 3, and our alpha is set at 0.05, right? So 3 degrees of freedom, that should be right here at the 0.05 level, is 7.815. That's the value that we're comparing. We've only got about a minute left before this cuts off, so let's compare that. Is 8.006 greater than that critical value of 7.815?
Yes.
Yes, it is. So therefore, we reject the null hypothesis. And in that case, we can conclude that there's a statistically significant difference between the levels based on gender at the 0.05 level, that 5% level of confidence. So I know going through 3 examples, that took us right up to the end. I know this is going to cut out in less than a minute. It's already telling me. It just doesn't tell me how many seconds we have left. But I do hope that—
3 on mine.
What's that?
It says 1 minute and 1 on mine.
Oh, okay. Well, it is going to cut out. I do hope that even just running through a few of those examples, I hope that I didn't confuse you even more. But do go through and watch the videos on chi-square. Go back and kind of rework these 3 example problems, and then go through and try the homework. As far as a tip for the homework, let's see if I've got my work here. Hey, I don't know where my homework problem is at. Well, I don't have my homework problem right here, so I don't think I can give you any tips on the homework just yet. I'd have to dig around for that, and then the time is going to be out. Do you have any last-second questions? Are you more confused than anything?
No,
I got the observed statistics. It's the expected frequency.